Bismillah ar-Rahman ar-Rahim. Today our first online session in the lab unit operation lab, CHE 235, and our experiment today for fixed and fluidized bed. Fixed and fluidized bed is a unit operation that's used in industry, and it's mainly used for application of industry for if I want to test the particles or want to treat the gas. So either I have a gas, I want to treat it, or I have particles, I want to treat it. So for example, if I have like a gas, and this gas, like natural gas, and this natural gas has a lot of contaminant in the gas, and I want to treat this gas. So I can put like a catalyst or particles, and this particle absorbs the contaminant from the gas. Also, for example, if I want to treat the particles itself, like I have like a calcium carbonate particles, and this calcium carbonate is used for many as a filler in many industry and many production, like paints and other things, and I want to coat this particle, so I can also use the fluid to coat this particle. So in order to reach the optimum mass transfer rate or mass transfer reaction between the particles and between the fluid, I have to reach the minimum, what is called minimum fluidization velocity. What is minimum fluidization velocity? We have the particles, there are between two forces. The drag force from the fluid from down to up, so this is drag the particles and force it to up, and we have the gravity force. It's due to the weight of the particle, so it's forced to go down. So our two forces, drag from down to up, and gravity due to the weight of the particles from up to down. When if the drag force higher than the gravity force, the particles will be fluidized. It will be like flowing through the medium. And if the gravity more than the drag force, so the particles is settled down and it's called fixed. Okay. Now, means fixed, that means particles are contacted to each other. There are no spaces between them, or they are reached to them. So when the gas flow, there's no reaction between the gas. The gas can't cover these areas because it's already closed. They are compacted to each other. And if the drag force higher than the gravity force, these particles can get out of the column. And also I can get extra, if I want to treat the gas itself, I can't treat it because more gas larger than the gas speed will be larger than the particle speed. So the optimum speed is when two forces are equal. The drag force are equal to the gravity force. So two forces are equal to each other. Now, so the optimum mass transfer will be at optimum fluid velocity when both drag force and gravity force are equal to each other. So pressure is the force over area. So we have gravity force minus drag force over area. So when the pressure drop when both forces are equal, it will be P1 minus P2. The density difference between the solid is the particles, and the fluid, LG is L is the height of the bed, and G is the gravity. 1 minus epsilon. Epsilon is the spaces between the particles, called porosity or voidage. Okay. So now we have the equation to calculate. This one is 1. If you epsilon equal 1 minus Lm over L, 1 minus epsilon m. M is a minimum. Okay, minimum. That means when at the minimum fluid drag force when it's fixed. That means when the fluid can expand. Once it's expand, so we have new. When the porosity increase, we have more spaces between them. Okay. So this is the pressure drop when both forces are equal. Now, now if the column is empty, the speed inside the column will be Q over area, or V dot over area. Okay, so this is the speed inside the column, and the area here will be the cross-sectional area by d squared over 4 because it's circular. This for plug flow. The plug flow means when the fluid cover all the parts in the pipe or the column. But actually in this experiment we have particles inside. So these particles inside prevent plug flow. So the fluid is forced only to pass through spores between them. So now the actual, as you know, when the area decreased, the velocity increased. So now the V interstitial velocity or the actual velocity will be the V superficial velocity divided by the voidage or the porosity. Now again, for the DH is hydraulic diameter. We can't use the D because now the D is not plug flow. We have particles inside and the fluid is not plug, the fluid only in the pores. So D become now new definition for the D will be D hydraulic for A over P. A is the area of flow and P is the weighted perimeter. So DH used for this packing for the fluidized bed, it will be DH equal DS. DS is the particle diameter, each particle diameter, times epsilon minus overall 1 minus epsilon. Okay, so the normal Reynolds number used is dV rho over viscosity. Now if we replace the D by the hydraulic diameter and we replace the V by the new V, it's V over epsilon, we will get the new definition for Reynolds number ds Vp over mu 1 minus. This is Reynolds number specific for the fluidized bed or for the porous medium in general. So now Reynolds number is ds, the particle size, times velocity, times density, mu, viscosity, 1 minus epsilon. This equation is for the pressure drop through the porous medium or through the fluidized bed, fixed and fluidized bed. So L is the height of the column, D is the particles, and epsilon is the porosity or voidage. Now, from this equation, we can calculate or find the friction factor for the porous medium or for the fluidized bed. This can be, since we can measure the pressure drop experimentally through the experiment, we can find the friction factor for porous medium. PM is a porous medium. So it's equal to pressure drop data, and by applying this equation, we can calculate the pressure drop. Okay. Why I'm doing this? Actually, I'm doing this because I want to find the minimum, the optimum mass transfer at minimum velocity, fluidized velocity. So I want to determine V. Okay. From empirical formula, they found that the friction factor for porous medium equal 180 over Reynolds number. We said Reynolds number is dsV rho and mu 1 minus mu. So we can, if we replace Reynolds number by this value, so we can get this new formula. This is the Reynolds number for empirical, and this one for when the fluid is laminar flow. Okay, since I'm looking for minimum fluid velocity, minimum means the fluid in laminar, not in turbulent. Higher speed will be turbulent, but I'm looking for minimum, so the fluid will be. So I'm using this equation. Okay, now this equation I just will replace the friction factor of the porous medium by that calculated from the Reynolds number. Okay, so by replacing, I will get this equation. This equation is just this equation, but I replaced the friction factor of porous medium by this equation. So this will be the new equation. Okay, This is my new equation. Now, laminar flow covered range of speed, okay? But my interest is to get only the speed that when two forces are equal. That means when the drag force are equal to gravity force. So this happens only when the pressure drop equal to this equation, as we said before. So I will take this equation and replace it into here, okay? To calculate only, make only the equation only for the when two forces are equal. So just I will replace this one by this one. So this will be my equation, okay? Now, so this equation represents the fluid or the fluidized bed only when two forces are equal to each other. So if I can now find velocity, so this velocity means the velocity when two forces are equal. That means at minimum fluidized bed. So V here will be, by replacing the equation here and remove the duplicates items, for example V and I, so by replacing all, so it will be V equal rho S. Rho S is the density of the particles itself, and F is the density of the fluid. If my fluid is water or gas or whatever, so it will be changed. G is the gravity, ds is the diameter of particles, and epsilon is the voidage or the porosity overall. So this equation is used to determine the minimum velocity required to start the fluidization. So this is empirical formula, it is used, and I can also get the actual minimum velocity if delta P by flow rate or velocity. So when the fluid come from down to up, it faces like friction between particles, so the pressure drop increase, and when more fluid increase, more friction as well increase and more pressure drop, until when the particles become loose. Okay, so that means no more friction between particles, so the pressure drop will be constant. At this point, the pressure drop will be constant, no more pressure drop because particles become loose and no friction between the particle surface and the gas. So the pressure drop will be fixed. So at this point, we can find the velocity by experimental way. So this is all about the fixed and fluidized bed experiment. Empirical formula we used to find the minimum fluidized bed. The also experimental way to find the fixed and fluidized bed. In the experiment now we will see the pressure drop. We have different type of particles and fluid. So for the fluid, we have two types of fluid. We have gas and we have liquid. When the liquid make fluidization for the particles, it's called particulate. When the gas make fluidization for the particles, it's called bubbling. Okay? So we will increase, and you will see that in the experiment. When we increase the flow rate of the fluid, you will see the pressure drop is increasing, and while the bed is fixed. Bed still have certain length until once it reaches the fluidization velocity. So you will find that the pressure drop become almost constant and the bed start increasing while the pressure drop almost any more pressure drop. And that's it about experiment today. And now we will see how the experiment looks and how we operate and see the data. That's it. Thank you. Okay, so now we'll start the experiment of fixed and fluidized bed. As you can see here, we have 3 columns. So each column has their particles. So here we have fine particles and coarse particles, and here also coarse particles. So that size is different. The particles here has the same particles here. So large, both are large particle size, but here the particle is very small, very fine particles. Also, the other difference is the type of fluid. here the fluid is gas, and as well the fluid here is gas. So in both columns, the difference between them is the particle size. So we can study the effect of particle size on fluidization process. This both column has the same particle size, but the difference between them is the fluid. So here we have a liquid fluid, this is water, and here we have the fluid of air. So the difference between them is the type of fluid. So now, as we said before, for the particles, when the air is the main fluid of the fixed and fluidized bed, the fluidizing process here is bubbling. Here the fluidization is particulate, because it's like particles is swimming in the fluid. Here is bubbling because the gas try to escape from the bed itself. So the gas when it come from down to up, it force or drag the particles up until it escapes, so it come down again. So here the fluidization here is bubbling, the fluidization here is particulate. So we now will start the experiment by the pump. As you can see, as you can hear, the sound of the water pump is open. So now we'll start the flow rate. Here we have water, air 1 and air 2. This is the water, this is air 1, and here's air 2. So this flow rate in liter per minute, and we have the pressure drop in millibar. So by increasing the valve, now start reading the flow rate. Okay, so here the height is almost same. There's no increasing in the height, but the pressure drop increase because there's a friction between the fluid and the particles. When we increase the flow rate, okay, increase the flow rate, now the pressure increase, pressure drop also increase, while the height is the same. The height doesn't increase. Now, again, okay, height is the same, pressure drop increase, the same. Okay, now at this point, as you can see, the bed expanded and the pressure drop, this is the last point of pressure drop. So when you increase, again, you see that as the flow rate increase, the bed expands, the height increase, while the pressure drop is almost the same. So when we increase the flow rate, the pressure drop, again, will increase the flow rate. See, the flow rate increase, the pressure drop, no more increase in the pressure drop, and the height as well increase. So this is for the first part of particulate fluidization. We'll close the pump, and now we'll start for the second part. Before starting for the second part, now the difference between them is only the size. Now, so we'll start with this one. Now, it's exactly the same like the water in terms of the process. So now, air 1, okay. Now the flow rate increase, there is increase in pressure drop. Here you can see any difference. The bed is still fixed because the gravity force of the bed is more than the drag force of the fluid. Again, I will increase the flow rate again. So by increasing the flow rate increase, and the pressure drop as well increase. The height of the column still fixed, not increase. I will continue to take the readings of the height, the flow, the pressure, and continue. Okay, so here no more increase, it's still fixed. Pressure increase, flow increase, bed is fixed until it reach a point. Now this is almost the minimum fluidized. You can see here this starts some vibration of the surface. So pressure drop is 41.5. This is the flow. When we increase the flow rate again, now this is the bubbling fluidization. So the pressure drop is around 45. When you increase, still the flow rate increase, the pressure drop constant. Okay? No more increase in the pressure drop. Also for the third one, okay, for air 2 is the same. Okay, now there is increase in the flow rate, the pressure drop increase until it reaches to fluidization. Once it reaches to bubbling fluidization, the pressure drop become almost constant, no more increase. So I'm increasing now, no more increase is the pressure drop. So what you need to take the height, to take the flow rate and the pressure drop every time until you get find the pressure is almost constant. So this is all your raw data. That's it. So now I'm closing the experiment. Okay. So just to cover what we said briefly, we have 3 columns. We have 2 types of fluid, gas fluid and liquid fluid. The liquid is water and the gas is air. And we have 2 types of size, particle size. We have small, very small particle size and larger particle size. And we test the fluidization process in the 2 types of particle size and 2 types of fluid. And in case of when the fluid is liquid, it will be particulate fluidization. When the fluid is air, it's bubbling, and you just see the difference between them in the process. And you also notice that there is no more pressure drop when the bed becomes fluidized, while the height increased. When it was still fixed, the pressure drop was increasing, while there is no increase in the bed height. So that's it. Thank you so much.